The important thing to remember about the linear functions was that they had a constant rate of change. Now another function that has a constant something about it is called an exponential function. That's where it has a constant percentage rate of change. So our first example, before we write the form of this, we want to do an example here. So we have a function at time t equals 0, a population, and we're calling it p of t now instead of f of x. But this shouldn't throw you, right? P is just the name of the function, just as f was the name, and t is the input variable instead of x. The input variable is called the dummy variable for a reason. It doesn't matter what it is. P of t, p of w, p of x, they're all going to be the same. Is 3,000, and the population grows 10% per year. We want to fill in the following table. So as we said, we're looking at functions in a variety of ways. We've already seen graphs and verbal, meaning the word problem, and a formula, and now we've got our table, so we've already covered all three of the different ways. So at time 0, the population is 3,000. We were told that. Now it grows 10% a year. So if you're like me, the way that you probably do this in your head is you say, what's 10% of 3,000? That's 300. I'm going to add that to the 3,000, and I'm going to end up with a total of 3,300 here. Mathematicians really like to do things with the least amount of effort, and especially the least amount of writing possible. So instead of doing this as a multiplication and then an addition, is there a way we can do it all in one step that combines the multiplying and the adding? And the answer is yes. You start with the 3,000 that you had, and you multiply it by 1.1. The 0.1 is like taking the 10%, and the 1 is like keeping the 3,000 that you already had. So after 1 year, we have 3,300 people. Now, if this were a linear function, we know that after 2 years, we would have 3,600 people because we go up by the same amount every time. But in fact, this is an exponential function. So now we're supposed to add 10% of this much. So 10% of this much is 3,300. Sorry, is 330. So we're going to take the 3,300 that we already had and add 330 to it. And now we'll get 3,630. And if we wanted to do this, again, with the least amount of work possible, we could be writing 3,000 times 1.1 times another 1.1. And writing two 1.1s next to each other is no big deal. But imagine by the time you get up to the 17th one of these, it would be a lot of trouble to write them all out. And it would be hard to count them, perhaps. So instead, we have, again, and this is another place where we see how good notation can really save us a lot of work. In this case, that 1.1 with a superscript 2 indicates that we're supposed to multiply 1.1 by itself. So 1.1 times 1.1. And then we're going to add 10% of this, so we're going to add another 363 people. So I think we'll come up with 3,993. That's a nice number. And that is like we took this number that we already had and multiplied it by 1.1. In other words, 1.1 times 1.1 times another 1.1. And then we write 1.1 cubed up there like that. And then it would keep going. And in general, the formula will be 3,000 times 1.1 to the t. And this is what makes this an exponential function. Not just the fact that we have an exponent, the fact that the variable is the exponent. So later on in the semester, we'll look at other functions that have exponents, like t squared or t cubed. But those are not going to be exponential functions. Those are going to be power functions, because what we need for an exponential function is to have the variable in the exponent. So just as we did with linear functions, we can now say what the standard form of an exponential function is. So p of t is an exponential function if it can be written just something as we just did. So the notation that our book uses is, for this value at the start here, they call that p with a subscript 0. And again, mathematicians don't want to use two syllables if they can avoid it, if they can get away with using one. So I will probably slip up, or not slip up, I will probably often call this p naught. Naught is another word that means none, so p sub 0 or p naught times a to the t. And remember, the variable is the t. And what is p naught going to be? P naught is the amount that you have at time 0. And we'll have an applet coming up where you can experiment playing around with different values of a to see how a affects the graph. Again, our little historical aside here. The first use of an actual superscript as an exponent came from a fellow named James Hume way back in 1636. And what I find interesting is that, so for example, if they had an a, they would write the exponent in Roman numerals. So instead of writing a with our 3 up there, they would write the 3 in the Roman numeral form. And they wouldn't ever write a with a 2 up there because that is actually more work than just writing 2 a's next to each other. So where we would write a squared, they would often just write a right next to each other like that. So that's the basic about what the form of an exponential function is. And now there are a lot of rules about exponential functions that I think you have probably seen over the years. So the first rule is when you have a to the m times a to the n. And I know that in the anxiety of a test, you might be confused and a little bit nervous and can't remember whether you're supposed to add these exponents or multiply them. And I have full confidence in you that you do not need to just guess. You can figure it out on your own. So try some example. So suppose you have, say, 4 to the 2 times 4 to the 3. Ask yourself, what does that mean? 4 to the 2 means you have 2 copies of the 4. 4 to the 3 means you have 3 copies of the 4. So altogether, how many copies of the 4 did you have? You had 5, which is what you get by doing what with the exponents? Not multiplying them, but adding them. So that's the rule there. A to the m times a to the n is a to the m plus n. So that's our first exponent rule. And again, really, you can figure something out like this. Now, it would be bad luck for you if you chose both of these exponents to be 2. So don't do that. Choose some other values. What if we have a to the m raised to the n? And again, let's try an example. Suppose that we had 4 to the 2 raised to the 3. What does this mean? 4 to the 2 means you have 2 4s next to each other. This 3 means you have 3 copies of that. So this is supposed to be 4 times 4, and then another 4 times 4, and then a third 4 times 4. So when you count up the 4s, how many 4s did you get? You got 4 to the 6th, and that's because what did you do with the exponents? You multiplied them. So that's our second important exponent rule. And our third is when we have a to the m over a to the n. So let's see what that would mean. So if we do an example there, suppose we have 4 to the 3 over 4 to the 2. And again, write out what does that mean. 4 to the 3 means you have 3 copies of 4. 4 to the 2 means you only have 4 of them on the bottom. So the natural thing to want to do is to want to cancel some of those 4s. So we can cancel those and those. And we're left with just a 4. But 4 is the same as saying 4 to the first power. And that's because what did you do with those exponents? You subtracted. So the rule is that this is a to the m minus n. Now, without having said it, what I was really assuming when I was writing out all of these copies of 4s here was that the values of m and n were actually positive integers here. Because, for example, if m here had been 1/2, what would it have meant to write out half of a 4 here? We don't know what that means yet. So these rules are great, and they make sense for positive integer values of n, but we need to figure out, of m and n, but we need to figure out what they mean, what happens when m and n are not positive integers. So our next thing will be just a very small step. We want to say what is the biggest integer that's not positive, and that integer is 0. So we'd like to see what do we mean by saying a to the 0. And I know a lot of you are saying, oh, I know that's supposed to be 1. And the question is, why is it 1? Is it just because somebody told you that it was 1? Or is there an actual reason that a to the 0 should be 1? And in fact, there is a reason, and we can get it from a variety of ways. But one way is to use rule number 3 here. So by rule number 3, I know that if I write, for example, 4 to the 2 over 4 to the 2, well, 4 to the 2 over 4 to the 2 should certainly equal what? That should certainly equal 1. But I like rule number 3, and I'd like it to keep working for all sorts of different exponents. And so what am I supposed to do by rule number 3? I'm supposed to subtract. So 4 to the 2 minus 2, which is 4 to the 0. So if we want to allow for an exponent of 0, and we want rule number 3 to keep working, we have to say that a to the 0 is 1. And we're going to just also say that a is not 0. 0 to the 0 is sort of a sticky subject. Different people define it different ways, depending on what their needs are on that day. So now we've got a to the 0. So we know what happens if we've got a positive integer exponent or 0. So the only other integers are the negative integers. So what if we had something like a to the negative n, where we're thinking about n itself as being positive? And again, we can use rule number 3 to figure out what this should mean. So by rule number 3, if I wanted to do something like, say, 4 to the 1st over 4 to the 3rd. So 4 to the 1st means I have 1 4 on the top, and 4 to the 3rd means I have 3 4s on the bottom. So that's just a complicated way of writing 1 over 4 squared, right? But by rule number 3, what am I supposed to do with these exponents? I'm supposed to subtract them. So I'm supposed to get 4 to the 1 minus 3. In other words, 4 to the negative 2. So if we want rule number 3 to keep working, and we do, 4 to the negative 2 is going to have to mean 1 over 4 to the 2. In other words, a to the negative n is going to have to mean 1 over a to the n. Otherwise, rule 3 stops working. So what exponents are left? We've covered the positive integers and 0 and negative integers. Well, there's actually a lot of numbers left. There are all of the non-integer rational numbers. So numbers like 3/7, 1/5, and so forth. So let's just first start with just a to the 1 over n. So a to the 1/2, a to the 1/3, a to the 1/4, that sort of thing. See if we can figure out what that should mean. So in this case, rule 2 tells us what this should mean. So if I were to write, for example, 10 to the 1/3 and raise that to the 3rd power. Now remember, we don't know what 10 to the 1/3 means yet. I mean, you might think you know what it means, and you're probably right, but we haven't really defined what it means yet. 10 to the 1/3, we're just going to write that symbol. We don't know what it means. Raise it to the 3rd power. By rule number 2, we're supposed to multiply those exponents. So when I multiply those exponents, I get 10 to the 1/3 times 3, which is just 10 to the 1st, which is just 10. So what that tells us is that we have discovered that if we want rule number 2 to keep working, 10 to the 1/3 must be the number whose cube is 10. 10 to the 1/3 is the number whose cube is 10. Well, I think that's a mouthful. The number whose cube is 10. We have a shorter way of saying that. We just call it the cube root of 10. So 10 to the 1/3 must be the cube root of 10. And so in general, a to the 1 over n has to be the nth root of a. So now that we know what happens when we have a to 1 over an integer, we'd like to figure out what happens when we have just a general rational number in the exponent, so like 5/31 or any other rational number you can think of. So a to the m over n, what does that mean? And we can use a combination of rule number 6 and rule number 2 to figure out what this means. Because by rule number 2, we can rewrite this as a to the 1 over n raised to the mth power. Wasn't it a good idea to choose two letters that sound so much alike? We can rewrite it that way by sort of doing this rule backwards. And then by rule number 6, we know what a to the 1 over n means. That means the nth root of a. But because multiplication is commutative, meaning the order doesn't matter, I could just as well have rewritten this as first a to the m raised to the 1 over n. That's also by rule number 2. And then now I can rewrite that as the nth root, because we know what that means from rule number 6, of a to the n. So, are there any exponents, any numbers that we can put in the exponent that we might want to put in the exponent that we haven't taken care of yet? We've taken care of all of the rational numbers. That includes integers. Integers are just a special kind of rational number. Well, yes, there's a lot of numbers that we haven't taken care of yet. They're all the irrational numbers. So some irrational numbers you might know are things like the square root of 2 or pi. So it's really going beyond the scope of this course to formally explain what we mean by that. But let me just give a general idea about what it would mean. What does 10 to the pi mean? And the nice thing is that we know how to approximate pi using rational numbers as closely as we want. We should write the mean there at the end. We know how to approximate pi as a rational number as closely as we want. We can write it as 3 or 3.1 or 3.14 and so forth. So I can write this. I can say 10 to the 3. And I know what 10 to the 3 means. And I can write 10 to the 31 tenths. In other words, 10 to the 3.1. And I know what that means by rule number 7 combined with rule number 6. And then if that's not good enough, I can write 10 to the 314 over 100. And if that's not good enough, 10 to the 3141 over 1,000. And if that's not good enough, 10 to the 31415 over 10,000. And I can keep doing that, and I can make this exponent as close to pi as I want by using rational numbers. And since I know what it means when I put a rational number in the exponent, whatever value this sequence of numbers is getting closer and closer and closer to is what we will define is meant by 10 raised to the pi. All right, I hope you enjoyed all of those rules as much as I did. So the rules really make sense. So if you forget one, don't just try to guess. You can figure it out by trying an example. And all of these rules, if somebody at one point just told you a to the 0 has to be 1, and they didn't tell you why, now you know why. It comes perfectly making sense from rule number 3. So the next thing we want to do is start to look at the graphs of exponential functions. And we have an applet for you to experiment with, changing the value of a and changing the value of p naught to understand how those affect the shape of the graph of an exponential function. So please try to experiment with that applet a little bit, and then we'll come back and do more with exponential functions.